Thank you for the instructions. First of all, I would like to officially to open the session 9.8 entitled Electrical Engineering. My name is Dardan Klimenta, and I'm professor from Serbia, and I'm with the University of Pristina in Kosovska Mitrovica. And today I will chair this session. The first presenter for today comes from Turkey, and I would like to call him Mr. Mehmet Ali Ozcelik. Are you here or not?
I am here.
Could you please share your screen with us?
Okay.
Welcome, please. Mr. Ali Ozcelik will present the paper entitled Modeling and Analysis of Transient Overvoltage due to Reclosing of Distributed Energy Resources. You have about 20 minutes to present your work, and please take your time, Mr. Ali Ozcelik.
Okay.
You're
Hello,
welcome.
Chairman of the session and my colleagues. First of all, I would like to thank the members of the electronic conference for organizing this beautiful conference and event and for giving us the opportunity to talk. I am a lecturer at Gaziantep University, Department of the Electrical and Energy. Today I will talk about modeling and analysis of transient over voltage due to reclosing of distributed energy resource. We have a PV model and the grid. The switching of the events is our idea, and the place of the load and capacitor is main topic of this study. I will first talk about introduction with the inclusion of the renewable energy source, the electric grid, microgrid, and distributed generation. It is more important topic. Inverter technologies are used to convert direct current produced by energy source, such as photovoltaic, to alternative current to provide grid integration. However, sometimes inverters, because of their non-reduction zones, like Dedek Island mode during reclosing at the breaker, such a situation could damage utility equipment and the distributed generator itself. Therefore, in the control hardware in the loop simulation study, we used Opal RT simulation hardware to do this and to produce best worst effect. We produced 180-degree out of phase closure on the utility and customer equipment, which is RL load and capacitors, were investigated according to line distance and location of the load. The simulation study was carried out in real time. Firstly, the simulation model was done in the MATLAB environment and then transferred to real-time environment. And we used physical inverter, which has 1 megawatt power, and to the use physical inverter, we should make EHS electrical model of the inverter to study with MATLAB and OPAL-RT. This is our real simulation hardware, and in the figure 1, the process of the real time. You need computation block and guy block. In this model, we make simulation model to work on it. The test on the applied system aim to verify the behavior of the inverter with the communication and interface between the simulator and the real-time control. Figure 1 shows the real-time system block structure. The subsystem here are divided into computation subsystem and graphics user interface subsystem, which are separately named as SM computation, which is slaver master subsystem, and slaver console. This is the other side of the block. The computation subsystem is responsible for numerical calculation. And this is EHS model of the inverter. The inverter is physically, we contained it to simulation environment. This model acts as the interface between the inverter hardware and software model, and is located into FPGA SM to be simulated for 1.5 microsecond time step. The EHS subsystem has inverter voltage routed to it and inverter current routed from it, acting as current source at the inverter connection point. This is our RL load model, which is three-phase transformer, and it has 1,600 active power and 600 reactive power, and is fed through the transformer. And our capacitor bank is power of 600 kVAr is used. The electrical power system is RL load, and capacitor group were tested at different location. And in the study, we used 9 scenarios to determine which condition is worst in terms of the transit voltage. And this is our electrical equivalent circuit. This side is grid and grid impedance, and grid line impedance, line 1 and line 2. And this is our capacitor bank. The other side is PV inverter. The left side is utility grid, right side is PV inverter side. And in the left, we used breaker to make reclose event on the line. And the grid voltage is 13 kilowatt, which is middle voltage. and short transmission length, source impedance, serial and parallel resistance, and the line, the length of the line is changeable. We used two line for the low line is 3 kilometer distance. For the long line, we used 6 kilometer length. There is also RL lot in parallel and transmission line are designed as line 1 and 2. The transmission lines are connected to 1 megawatt inverter over the grid, our model. This is theoretical background of the study. You see here capacitor in the LC circuit. The capacitor voltage for classing of the switch is given first equation, where is this is capacitor voltage and time grid voltage amplitude and resonance frequency of the capacitor. After the substation of VC0 is equal to minus V for the initial 180 degree voltage on the capacitor. We closed the breaker 180 degree. Why? Because we want to see worst transit voltage. So when we close the breaker at 180 degree, we produce worst transit voltage. This equation shows that the peak voltage on the capacitor bank reach 3 per unit, which is consistent with the result of the study. And we see is here where V times 1 minus 2 cosinus omega t, because the resonant frequency is also important to this study. And we wrote the equation, and resonance frequency and damping factors are important in terms of the transit peak voltage. We firstly calculate the damping factor and accordingly peak voltage with the equation, and then we made real-time simulation to compare both of them. And according to first scenario, we calculated 30,000 about 30,000 volt peak voltage, and the position, we change position of the capacitor group and RL lot, position 1 and position 2. In the position 1, the balancing capacitor is placed the grid connection, and PV inverter and load are connected at the far end due to 185 phase differences of 6 kilometer line. A very high inrush current to the circuit and overvoltage have occurred due to the inductance and the main supply and the capacitor bank. As a result, voltage and current 1 kilohertz oscillation occurred. And you see here the place of the capacitor and load is on the U, and this is middle of the line, and this is place of the inverter. Now we are here, which are capacitor and RL load are in the same place, which is next to grid, main grid. And accordingly, this is simulation, real-time simulation figure, and we see is here. We have about 30,000 peak voltage. In the second scenario or position, we change of the place of the capacitor and RL load to high, which is near the PV inverter site. And we see is here our voltage of the capacitor is 28,000 voltage. The voltage change on the capacitance after the reclose according to position of the capacitor and RL load. The transient peak voltage fall on the PF power factor capacitor is 28,000 volts. Accordingly, we wrote the convolution. The control hardware is popular. Simulation is recently and is used to simulate behavior of the PV inverter in real time. Again, our PV inverter is a physical inverter, real inverter, and we put in simulation. This is important site. This approach adds complexity and simulation, but ensures that the PV inverter's response is correct. Modern solar inverters contain many controls, loops, and protection functions that are difficult to capture in a virtual model. In distributed energy system, there is possibility of out-of-phase reclosing. The literature states that the worst case scenario is 180 degrees out of phase lasers. With the work voltage transit effect on the RL and C capacitor loads were investigated in the worst closed condition and demonstrated on the capacitor. The equivalent circuit of the electrical power system was drawn and its parameters were calculated. The damping effect on the line and capacitor is essential, and the inrush voltage current values change according to this effect. Reducing the distance of the equipment to the breaker increases its exposure to dangerous high transit electrical values. When the obtained transit voltage values are examined, it is seen that they vary between 2 per unit and 3 per unit. The change of the transit effect according to position of the loads on the line and the damping situation and resonance frequency has been realized in real-time simulation. And thank you for your attention.
Dear Mr. Ali Ozcelik, thank you for your presentation. Now we will ask our colleagues, do you have any question for Mr. Ali Ozcelik related to the paper presented? It seems that there are no questions for you, but I will ask one simple question. Related to slide 3, you showed real-time simulation hardware on it. Is this installed like a microgrid in your lab or no?
Yes, this is a microgrid laboratory, and this is a microgrid system. In the Ruppert, we see here simulation hardware. On the simulation hardware, there is a inverter, but I didn't show it in the simulation.
My right question is, you have a 1 megawatt inverter there, and you really
Yes.
perform simulation with that inverter.
Yes, we used 1 megawatt inverter physically, and we modeled this inverter in MATLAB and to connect between simulation hardware and real inverter.
Thank you for the response. You have really good conditions to do experiments in your lab. Thank you, Mr. Ozcelik, for your presentation and your work. The next presenter comes from China, and according to our order, this paper should be the first one, but now we will start as the second one. Are you here, dear colleague Dan Liu?
Yes, can you hear me?
Yeah, we can hear you. Now we can see you as well. You're welcome, Mrs. Dan. And I will now introduce you. You come from China, and you will present the paper entitled Distributionally Robust Collaborative Dispatch of Integrated Energy Systems with DNE Limits Considering Renewable and Contingency Uncertainties. Please take your time, and in the next 18-minute present here. Welcome.
Hello, everyone. Today, I want to share the topic of distributionally robust collaborative dispatch of integrated energy systems with DNE limits considering renewable and contingency uncertainties. My report is divided into 4 parts. Part 1, background. Multi-energy interconnection region contains 4 kinds of energy form: cold, electricity, heat, and gates. Integrates all kinds of energy supply equipment in the regional energy station and makes a unified operation schedule by information technology and the Internet of Things to achieve the goals of energy supply optimization. CCHP system as a typical representative of multi-energy interconnection region has become an important means to improve energy utilization efficiency, solve energy storage and shortage and environmental pollution issues by its high energy consumption efficiency, flexible and reliable energy supply mode. The combined heat and power unit has the characteristics of quick start and stop, which can effectively mitigate the fluctuation of renewable output and is considered as the key coupling elements to facilitate the renewable energy consumption. However, the increasing penetration of renewable energy may bring an immense challenge to the safe and stable operation of integrated energy system. The following 3 problems remain unsettled: It is shown in the PPT. First, challenges the decision-making results obtained by robots optimization can be too conservative, while the probability distribution of renewable energies is difficult to accurately estimate. Two, the uncertainty of contingency events such as equipment and line outages is not considered in the dispatch mode, which may affect the stability of system operations. Considering the renewable energy as the new dispatchable resources, it is too costly to balance the power load mismatches by regulating other dispatchable resources, especially in the case of high proportion of renewable integration. And according to these challenges, we have three solutions, such as apply the distributionary robots optimization, establish an adjustable ambiguity set, and we also propose the concept of do not exceed limits. Part 2, what did we do? The goal of optimal dispatch mode of IES is to minimize the optional cost by considering the fuel cost, startup cost, and spine reserve cost, which is subject to the following technical constraints, including both the unit and the system constraints. Ambiguity set characterizing renewable power based on the measures is presented, where the empirical distribution of renewable output is used as the reference to estimate its actual probability density function. We further present an adjustment uncertainty set to characterize the contingency probability of both the generation CHP unit and the line outages. This paper presents a two-stage distributionally robust optimal dispatch mode of spiny reserves and DNE limits in IES, considering the uncertainty of renewable energy and the system contingencies. The two-stage decision-making structure can be expressed in the following mini-max-mini form. The objective function of the second stage is to minimize the regulation cost of the unit. To solve this problem, we apply the duality theory and KKT conditions to transform the whole optimization problem into a single-level mixed integer linear programming model, which can be directly solved by commercial solvers such as CPLEX and Groby. This page shows the application architecture of how to deploy the prospered dispatching model for real implementation. Client sides offer lots of data through application programming interface. We transform the data into our model. In our model, include functions of forecast and solver. This page implementation process including 3 steps. First one is schedule preparation. This full work is done online. Okay, let's go to the second step. Schedule execution. Divided into 2 levels. Firstly, power down information is divided into provincial load decomposition and local load decomposition. Here we should notice all users' events notification and its executive monitoring. Send the instructions to the terminal and enter into real-time monitoring. After the event's over, we should do effect evaluations and event info. At the last, it is a simulation statement. Let's go to the smart terminal deployment. The communication, measurement, and control is the 3 basic functions. It can communication with lower systems like smart meters, heat pump, and micro turbine, with upper systems like master station and building automation system. Also, it can get energy data from smart meter. It can control heat pump, PV, micro turbine, and other energy supply devices. About the advanced applications, it has operations strategy management, response capability assessment, and response command execute. Part 3, case study. The test integrated energy system is illustrated in Figure 1, which consists of an IEE 33-bus power distribution network and a modified 33-bus heating network. Its generational contains 3 CHP units, 2 energy storage systems, 2 electrical boilers, and heat storage tanks, 1 wind farm, and 1 solar photovoltaic plant. The CHP unit with flexible and adjustable energy conversion ratio is considered as the slack bus. The prospered MILP model is solved by CPLEX, and the computer's information is shown in this part. For comparison, 3 scenarios are stated in the paper for analysis to verify the effectiveness and reliability of the prospered mode. Case 1, Case 2, and Case 3, we also call the DROD model, DROD CP model, and DROD CP DNE model. To investigate the influence of renewable and load uncertainty on the dispatch results, we assume that the fluctuation covers 20% of forecasted value, which is shown in the Figure 2. The expected system span reserves renewable energy utilization ratio and load serving ratio under the 3 cases are compiled and analyzed. The numerical results under the 3 scenarios are given in the table. We can see in this part. It can be seen that When considering the uncertainty of system faults, the overall spine reserve capacity of the DRODCP and DRODCP DNE model is higher than that of the DROD model. Figure 3 and Figure 4 outline the detailed energy dispatch results of Case 3 in the power distribution network. Figure 5 and Figure 6 illustrates the centered dispatch results as well as its maximal amount of variation for heat network. Figure 7 represents the allowable wind power access rate for wind farm. As depicted, the DRODCP DNE model allows for a wider range of wind power access compared to the DRODCP and DROD models. This is because the DRODCP model takes into account the randomness of equipment failure, resulting in an increased demand for renewable energy and indirectly allowing for a greater amount of wind power to be connected to the system compared to the DROD model. To study the impact on system operation on the different control parameter tau, we mainly focused on Case 3, the DRODCP DNE model, and the relevant experimental results are shown in the table with increasing value of tau. It can be seen that the reliability and economy of the model can be controlled by adjusting the parameter. The next part is the conclusions. These three conclusions from the paper are shown in the picture. First, by accounting for the system contingency uncertainty, the distributional robots cooperative model can simultaneously optimize the spine reserves, improve the utilization rate of renewable energy, and enhance the robustness of the system. Second, the proposed collaborative optimization mode can greatly broaden the feasible range of renewable energy integration into the system by co-optimizing the do not exceed limits, thereby achieving a more favorable trade-off between the overall operation cost and the utilization of renewable power. Last, the reliability and economy of system can be adapted by tuning the adjustable parameters of ambiguity set of contingency properly. That's all. Thank you.
Thank you, Mrs. Liu, for the presentation of this very interesting work. Any question for Mrs. Liu related to the presentation? It seems that there is only one question from my side for you. Dispatch problems always are linked with the use of meta-heuristics. Did you use meta-heuristics for your optimization in this specific case?
Yes, but we use this two-stage model is the optimal model that we can solve this problem by games use the commercial solver such as the CPLX and Groby. If we consider more limits or more conditions, the model will be too difficult. That we do not have good methods to simulate it, so that games cannot directly solve it.
Okay, thank you very much for your response, dear Mrs. Liu, and congratulations for good work. The next presenter comes from Estonia. And are you here, Mr. Asefi? Do you hear us? Could you please repeat? We didn't hear you. Do you hear us?
Is it possible for you to hear me?
Now is better. We can hear you. Welcome, please. Mr. Sajjad Asefi will present the paper entitled Incorporating Service Type in Aging Failure Model of High Voltage Circuit Breaker. Please take your time and try in the next 18 minutes to present your work. Welcome, please.
Right. I'm not sure if you can see the screen at the moment.
Yeah, we can see yours.
All right. Thank you, Mr. Chairman, for the introduction. I hope you can hear and see my slides. My name is Sajjad Asefi. I'm from Department of Electrical Power Engineering and Mechatronics from Tallinn University of Technology, Estonia. And today, on behalf of the co-authors of this research work, I'm going to discuss with you the topic called Incorporating Service Type in Aging Failure Model of High Voltage Circuit Breakers. The presentation outlines would be after introduction, I will discuss with you the aims and objectives behind this work, and later on the proposed methodology, and at the end we would have the results and the conclusion. So briefly regarding the introduction, generally we can divide the power system, the equipment, especially in the power system, into two categories called primary system and the secondary system. In the primary system, we would have devices that are in direct contact with the energy flow, such as generators, power transformers, and circuit breakers, also in the, and so on. And in the secondary system, which is more related to the protection and control, we would have instrument transformers, protection relays, metering, and so on. But today's focus and my research work mainly is high voltage circuit breakers, which, as you know, are essential components for reliability and resiliency of the power system. What would be important to take into account that the work is mainly related to, would be an assistant to the maintenance strategy for the system operator. So I thought it would be of great importance to know that we have different categories of maintenance strategies. We have corrective and preventive. In corrective maintenance, basically, we wait till the device fails in the system and then we change it. But in the preventive maintenance, we have three subcategories. It can be time-based. It means that after, for example, 1 year, you are going to do the maintenance for the power transformer, let's say. Or we have condition-based, based on the condition, or if the temperature increases in the power transformers, you decide when to do the maintenance. And at the end, you would have a reliability-based maintenance that you consider the historical data and reliability indices to do the preventive maintenance. The focus of my work mainly is on preventive maintenance and reliability-based. So here is the figure for a 110 kV high voltage circuit breaker in the substation. As you can see, we have three main parts for the high voltage for the circuit breaker. We have the insulation medium, which in this case is filled with SF6 gas. Then we would have drive or operating mechanism, and at the end we would have the secondary and auxiliary circuits. Based on the SIGRE statistics, the latest SIGRE statistics, which was published in 2012, the main for SF6 high voltage circuit breakers, the main cause of the failure is related to the drive and operating mechanism, which is approximately 40%. Then we would have insulation medium, and then we would have secondary and auxiliary circuits. The failure modes, also the major failure modes for the high voltage circuit breaker can be divided into three categories. We can have mechanical failures when the circuit breaker does not open or close on command, or it opens and closes without the command. We can have electrical failure modes, which are mainly related to the making or breaking or the resistance of the contacts of the high voltage circuit breaker varies and cannot carry the current. Or we would have the insulation problem, which can be leakage of SF6 gas, or it can be external, such as breakdown across the poles of the circuit breaker. In the figure left-hand side, you can see based on the statistics, we would have if the service type, or let's say the place where the high voltage circuit breaker is going to be used is important in the number of operations it's going to have. By the operation, I mean close and open operation. And then we would have, if we use circuit breakers for shunt reactors, we would have more operations than when we are using it for the cables or for the transformers. On the other hand, in the right-hand side, you would see the major failure frequencies per kind of, or service type, or kind of service that they are going to use. As you can see, if you use circuit breaker for shunt reactors, let's say, you would have more failure rate compared to the other type of service types. So what are the aims of the objectives of this research? First of all, we need to know that the aging failure model would be helpful for the maintenance strategy, as I mentioned already. So in this work, I'm going to use the historical data to estimate the remaining useful lifetime of the circuit breaker, which would be an assistant for the system operator for decision making, or as a decision support. What we have used in this work is the Gaussian function-based model, and what we have done is to incorporate service type. Since it has, as you saw in the previous figure, it has a considerable effect on the major failure rate. What is MAF abbreviation is for the major failure rate, and what is referred to is the failure that terminates one or more core functions of an equipment. So a little bit of background regarding the reliability of mainly in the reliability area, we would have a failure rate, which is presented by the symbol lambda, and it refers to the number of failures of the equipment per unit of time. So on the other hand, we would have another index called mean time to failure, which is more understandable, and it specifies the time that we are expecting, the mean time that the device is going to fail, or if the device is repairable, it's also known as mean time between failure, and it's 1 divided by lambda. And the overall lifetime of the equipment in the power system is normally shown with the bathtub curve in the figure, as you can see below. We would have the black curve is the overall failure rate, but what it consists of is that we would have failure rate in the early stage failures that are high initially, and then they decrease, and then we would have aging failure that with time it increases, and then we would have random failures that are constant during the time. And this summing up these three failures would result in overall failure rate as shown in the black, and its famous bathtub curve. Normally in the literature, we have Weibull distribution. I just provided the equations for the Weibull distribution. As you can see, we have different parameters for the Weibull distribution. Why it is very famous in the reliability engineering? Because it's flexible and can be related to the other distributions as well. And for example, if the scale parameter is equal to 1, it would we have the similar behavior to exponential distribution. Also, we would have, so What we used, let's say our work was inspired by the Gaussian distribution. The main function of Gaussian distribution, as you can see, is presented above. What we did, we tried to use the summation of two Gaussian functions and to fit the data, the mean time to failure data of high voltage circuit breaker that we had from Sigre statistics, and try to fit our model as presented below. So, and we could try to compare this model with the conventional models, such as using R-squared method. And also, in order to incorporate the service type, we need to normalize the failure of the service type. So we use Z-score method to do this. As you can see, the equation is provided. So the final equation for the mean time to failure is what is presented below. To demonstrate the results in the left-hand side in the table, what you can see is the age of the device and the failure rate, and the mean time to failure, which in the figure are shown with the red triangles, red yellow triangles. And then we tried to fit variable distribution and exponential distribution and these data. However, in the proposed, also we proposed the summation of two Gaussian models. We try to fit the data with this summation, and as you can see, it fits very good to the proposed data. Based on this obtained model, we expect, for example, and based on the available data, we expect the remaining useful lifetime of the device to be around 45 years. Here in the table also above, you would see the R-squared value applied for the models compared to different exponential and variable distribution. The proposed model has a higher R-squared value. If the value of R-squared is close to 1, which means the better fit to the data, as you saw in the figure, it was better fit. As I mentioned, we incorporated the service type also. So if the age is around 45 years, if it is used for the cables, you expect that the circuit breaker is aged more. However, if it's used for shunt reactors, after normalization, you will see that, okay, it's going to be around 38 years or even less, depending on the condition of the circuit breaker. But this is how we incorporated the failure, the service type also in our results. So what we presented was a novel model to estimate the remaining useful lifetime. And the proposed model was inspired by Gaussian distribution function. What were the data we used? We used the Sigre survey data, and we converted the failure rates to mean time to failure. And the model was the model that fitted on the data. The proposed model demonstrates a better accuracy based on the R-squared scheme. And also we incorporated service type of the high voltage circuit breaker to avoid underestimating the failure characteristics of the high voltage circuit breaker. And what would this lead is to provide a more realistic measure of the remaining useful lifetime for the circuit breakers. All right, I reached the end of the presentation. Thank you very much for your attention. If you have any question, I would be happy to answer.
Mr. Asefi, thank you very much for this interesting work and your presentation of it. Any question for Mr. Asefi? It seems, again, I will ask only. On one of your slides, where you presented the major failure modes, could you show it again? You divided the failures on electrical and insulation.
Yeah.
Could you please, according to my knowledge, and insulation failures also are covered with the electrical ones. How divided you that on electrical and insulation failures?
Yeah, thank you very much for the question. Actually, so in the Sigre statistics, they try to do this division, and also I try to follow the same. But it's understandable because in the insulation scheme, in the internal insulation, we have the chemical material such as SF6, for example, or if it is oil, or it can be vacuum, or it can be air also used for the arc extinguishing medium. So if something is happening in that area, the internal or across the poles, that is called for the insulation. However, for the electrical part, what is main focus is the contacts, electrical features such as resistance of the or misalignment of the contacts inside the circuit breaker. So this is the division basically has been made, and the main point is because of SF6 gas. So in case we have leakage of SF6 gas, it also affects, it's kind of counted as the insulation.
Yeah, okay, because according to my knowledge, always failures with insulation correspond to the electrical ones. Thank you again for your question and explanation of this. Congratulations, and we will continue with our session. Thank you very much, Mr. Asefi. The next presenter is the same one like previously, comes from Turkey. Mr. Ali Ozcelik, are you here again or no?
Yes, I am here.
Okay, we are hearing you. Could you please take your time and present the second paper entitled Experimental Investigation on Change in Iron and Copper Losses in the Transformer? Welcome, please.
Thank you.
And a little bit, if you can speak quicker, because time is gone.
Okay, thank you.
Thank you.
The name of the study is Experimental Investigation of Change in Iron and Copper Losses in the Transformer. And you know the transformer is essential in the energy conversion system. So we evaluated the study of working of the transformer. You know, we started with the introduction to understand the base of the study. The idle run test in transformer is done to find the iron losses of the transformer. In the no-load test, the secondary winding end of the transformer are open circuited, and the rated voltage is applied to the primary winding ends. Since the current drawn from the grid in the idle operation is small, no-loaded copper losses are neglected, and all idle power drawn is considered iron losses. The study examined the variation of the iron losses at various voltage applied to the transformer primary winding. The iron losses showed a nonlinear characteristic with the applied voltage when a load is connected to the secondary winding of the transformer. It has been observed that as the load increases, the iron losses do not change depending on the load and remain constant. Short circuit test find copper losses in the transformer. The test is done from the primary or secondary side of the transformer. Iron losses are neglected since the applied voltage is small in the quick circuit test. The copper losses at various loads were calculated by increasing the load connected to the secondary transformer. We made two experiments. First is idle working of the transformer. In the second is short circuit. In the idle work transformer, this is a picture of the transformer which is used in the experimented. In the idle run losses by running the transformer unloaded. this power is equal to iron losses and hysteresis and Foucault loss. There is two pictures here, the connection diagram of the idle and short test. In the idle test, it is considered the power is equal to iron losses. And iron losses depend on the frequency and voltage because in the idle test there is no more current. So we can say the power loss is equal to iron losses. In the short test connection, we couldn't increase the voltage because of the heat. So in the short test, the power loss is equal to copper loss. And according to the experimental results, we produced this table. And according to the figure shows the variation of the copper losses according to primary voltage. Again, it is seen that the variation of the copper losses is nonlinear and has a very low value. The variation of iron losses according to the primary voltage, as the voltage increase, it is seen that the total losses reach the iron loss value. This is the result of the idle run test figure. Since the energy component of the idle current is small because of the no load, the reactive part is large and the no load power coefficient is consistently will be low. Therefore, the standard deviation value of the active and reactive power in the idle test were 6.62 and 13.92 respectively. And the idle test is short circuit. You can see here the voltage is very low because of the depend of the current, and the short circuit test, the values taken from the short circuit test of the transformer and the calculation parameters according to impedance and conversion coefficient. According to the conclusion is in the transformer, the iron test is done to find the iron losses of the transformer, and the short circuit test is to find the copper losses. In the study, iron losses and no-load copper losses were found from the no-load test of the transformer. It has been determined that the copper losses are minimal at no load, and the iron losses show nonlinear increase according to applied voltage. According to the results obtained, it is predicted that most of the energy lost in the operation is due to high hysteresis and Foucault losses, while copper losses are negligible. The standard deviation values of the active and reactive power in the idle test were 6.62 and 13.92 respectively. The short circuit test found the impedance value of the transformer. In addition, the short circuit test found copper losses. It was determined that the copper losses increased non-linearly as the load increased, and the iron losses remained constant as the load increased, because iron loss depend on the voltage under the short circuit study, and with this study, I think the working of the transformer can be more understandable, and it can contribute in terms of the transformer to more understand. And thank you for your attention and patience.
Thank you very much for your presentation, Mr. Ozcelik. Any question for Mr. Ozcelik related to the presented work? It seems again only I have questions from for presenters.
Okay.
According to the content of your presentation, you investigated experimentally change in iron and copper losses of the power transformers.
Yes.
And this topic is for years exploited topic by researchers worldwide. And just one question related to the application of your results. Did you try to put the results in equivalent scheme and to get some analytical results and to compare them with the experimental ones? Each transformer has its own equivalent circuit. And
I calculated with the theoretical background, and I find experimental, but I didn't make comparison exactly number. Maybe good idea to develop, improve the study.
Okay. Okay.
The paper contains both results, theoretically and experimentally, but there is no comparison with the experimental and theoretical. And it is good idea. I think we can add to improve more the paper.
Okay, thank you very much, dear Mr. Ozcelik. You're welcome. And then we have just one presenter for the end. Mr. Povilas Marciulionis, you are here, as I can see. Welcome, yes. Please.
Hello.
And good afternoon. Hello. Mr. Marciulionis will present the paper entitled Analysis of DC Corona Discharge Electric Field and Electrohydrodynamic Airflow. Take your time and welcome. And please present your work in the next 11 minutes.
Okay, thank you very much. I will try. Hello, my name is Povilas Marciulionis, and my paper is analysis of DC corona discharge electric field and electrodynamic airflow. And corona discharge ionizes air molecules near the high voltage electrode. And that causes ion movement from one electrode to another, and charged particles move along electric field lines, and neutral particles move in together with airflow. And direct current corona discharge is used in many industry applications to charge small particles or liquid droplets and to control trajectories of their motion. Wire-to-plane electrode system is mostly used to cause the particle charge transfer that is applied in many technologies, such as particle separation, mixing, cleaning, or deposition. In the paper, there is method of corona field calculation is proposed. Suitable boundary conditions are investigated. Two-dimensional numerical model for computation is presented, and method of the electrodynamic airflow calculation is proposed. So first of all, there is we need to talk about boundary conditions when we calculating in numerical methods, and there is electrode system. The high voltage electrode is wire, the small one, and the ground electrode is plain. And boundaries, second boundary is open boundary. That means the flux through that surface is equal to 0. And symmetry line, that means also the flux doesn't goes from that symmetry line. The other boundary conditions is on the corona electrode surface, electric field must be equal to electric field calculated by Peake's equation, and this must remain the same in all boundary. So to make it, I found the calculation that there must be density of charge must be calculated by this equation to take the set of electric field. So does the electric field exceeds maximum field strength value determined by Peake's law is checked. If true, the space charge density is increased by small value at that point and during to the next iteration. If electric field strength becomes smaller than Peake's value, then space charge density is reduced at that point by small value, and corona discharge starts always at the point A. The A point is this near to the plane electrode. Because this point is closer to the grounded surface, although all wire points have the same potential value, the normal projection of electric field strength at the surface of corona electrode is not the same at the beginning of corona discharge. Space charge density occurs only in the place where the electric field strength exceeds Peake's value, and iteration process ends when electric field strength at that point of corona electrode becomes not greater than 1% of absolute difference from values determined by Peake's formula. Yeah, I hope I explained the calculations. And I used the formulas to calculate potential in all spaces. I used Poisson equation that takes form in two-dimensional space. And for charge conservation equation, I used to calculate space charge distribution. And column force has 3 projections because the force depends from current density divided by mobility of ions, and there is convection current, drift current, and diffusion current. That's we have 3 projections, and there is results of computations, and there is space charge density distribution between the electrodes at the different voltage values, and there is starts from 5 to 10 kilovolts, and space charge density distribution is gradually when applied voltage is low, near the 5 kilovolts, and density really distributed near the surface of corona electrode. When applied voltage is high, yes, space charge density is densely distributed near the surface of corona electrode. Variation in space is intensive and value decreases much faster in comparison of low voltage cases. The next is volume force distribution at 10 kilovolt voltage, and the vectors shows force magnitude and direction, and coloring represents force magnitude. From the figure, it is clear that corona field force is acting in small space between electrodes, and distribution of force is very heterogeneous. The greatest value achieved at lowest point in the wire, this point. Although small amount of power remains in all inter-electrode space, but it has negligible influence to the electrodynamic airflow distribution or velocity magnitude. And there is electrodynamic airflow computation system, and I use Navier-Stokes equations and fluid continuity equation. For this, I use boundary conditions, and boundary conditions that the fluid temperature, pressure, and density are constants. Vx and Vy are air flow velocity to x and y directions, and Ni is kinematic viscosity coefficient, and solution is made by single phase laminar flow to ensure stability of solution, because it is very unstable. So I use isotropic diffusion Turing parameter, and also use pseudo time stepping. Because when we use pseudo time stepping, we have smoother solution without fluctuations, and maximum number of iterations I changed to 100 to obtain convergence of the solution, and number of pseudo time stepping can be changed with different mesh or voltage values to find a suitable to solve the problem. Boundary conditions for the computation of electrodynamic airflow distribution are the surface wire electrode and this and this. On the electrode surface, the airflow equal to 0. On the symmetry line, Vx equal to 0. That means there is no flow through the symmetry line. And maybe that's all. We have results. It could be noticed from the figure that airflow distribution character is the same, but with rising velocity, airflow circulation circle is expanding compared to low voltage cases. And maximum value of Y direction reaches below the varia. Below the varia means the red places, yes. And maximum values to X direction reaches above the plane, approximately distance of H from the symmetry line. I mean, these points are here. And conclusions. Suitable boundary conditions of discharge electrode are investigated. Two-dimensional numerical model for computation of direct current corona field in wire to plane electrode system is presented. The numerical modeling data of space charge distribution is presented. To calculate airflow distribution in DC corona discharge, this console multiphasic program is proposed. method to stabilize computations because it's very heterogeneous, and volume force distribution in inter-electrode space is introduced. And that's all. Thank you very much for your attention.
Dear colleague Marciulionis, thank you very much for your presentation and interesting work. Dear colleagues, do you have any question related to the topic presented now? It seems at the end only my questions are here.
Yes.
Dear colleague, could you please say us, did you simulated this corona phenomenon in the COMSOL or no?
Yes, in COMSOL multiphysics program. This
Which
is
version, please?
Version was the 4.2, I think. 4.2.
4.2. Also, I use the same version and
Okay.
the dot 3. A little bit older versions, but what to do? Did you have possibility to compare your results with some results from the practice, some measurements of corona phenomenon?
Yes, I measured voltage and current. I can measure. Yes.
Okay.
And if we integrate the electric field and space charge and mobility of ions, we get current. So we can measure it and to compare.
Okay. Thank you very much, and your work was really interesting and useful for practice. And now remained only 8 minutes to end this session, and my duty is to open discussion about all the presentation presented now within this session. Do you have any question for presenters or no? For me? It seems that there are no questions, but the next step is to conclude this session. It was my pleasure to chair this session entitled Electrical Engineering. All five presenters from China, Turkey, Estonia, and Lithuania presented their works. Also successfully answered to my questions, and I hope this sharing was interesting for all the attendees and the presenters. And at the end, just to say what this is Darius. We have just 5 minutes up to the end.
I think everything was perfect. And,
I can conclude this session. And
yes.
Thank you very much to everybody. And officially, this session is concluded now. Thank you. And to you.
Thank you to everyone, and for Mr. Chairman as well.
Thank you.
See you.
See you next time. Bye-bye.
Bye.